Let us learn color in organic compounds. In organic chemistry, the color of compounds arises from the absorption of light in the visible spectrum, which is related to the electronic structure of the molecule, particularly in the presence of extended conjugation, which is the alternation of single and double bonds. Compounds with extensive conjugation absorb light at higher wavelengths, extending into the visible region, causing them to appear colored. Thus, the color of organic compounds determines which wavelengths of light are absorbed and therefore which wavelengths are transmitted and perceived by the eye. The color of organic compounds is primarily determined by their structure, specifically the presence and the extent of conjugated system, alternating single and double bonds, which allow for the absorption of visible light, leading to various colors. The molecule usually contains an alternation of single and double bonds known as conjugated systems. Most simple organic compounds with a few multiple bonds are colorless or white because they don't absorb visible light. However, when multiple bonds are conjugated, which is nothing but alternating single and double bonds, the energy gap between the highest occupied molecular orbital, abbreviated as HOMO, and the lowest unoccupied molecular orbit, LUMO, what we call this LUMO, and this is HOMO, decreases. This allows the molecule to absorb light in the visible region, UV beams, instead of just the UV region, leading to the appearance of color. The longer the conjugated system, the lower the energy required for absorption, and longer the wavelength of light absorbed, which can lead to a shift in the perceived color. In UV spectroscopy, the color of an organic compound arises from the absorption of light in the visible region. The color of an organic compound is related to its electronic structure, particularly the extent of conjugation in its molecules. Color in organic compounds is associated with unsaturation. A compound's color arises from the absorption of specific wavelengths of visible light, with the perceived color being the complementary color of the absorbed wavelengths. Extended systems of conjugation in which the alternating single and double bonds are present and they allow the molecule to absorb light in the visible region. Eventually, it leads to a colored appearance. For some compounds, the radiation in the visible region of the electromagnetic spectrum is sufficient to promote electrons to an excited state, and consequently these molecules are colored. Tetrazine consists of bright orange crystals because the compound absorbs light from the blue end of the visible spectrum. A carbon-carbon double bond in ethane, for example, absorbs energy as electrons in 5 bonds are promoted to higher energy levels. Conjugation and color. The presence of conjugated pi bonds, which is nothing but alternating single and double bonds, in a molecule is a key factor in determining its color. These conjugated systems allow the molecule to absorb light in the visible region, leading to certain color. The extent of conjugation affects the wavelength at which the absorption occurs. When white light, which contains all colors, strikes the compound, some wavelengths are absorbed and the remaining wavelengths are transmitted or reflected. The color we perceive is the result of the wavelengths that are transmitted or reflected. Absorption and perception. When a molecule absorbs light, it excites electrons to higher energy levels. The remaining wavelengths of light Those not absorbed are transmitted or reflected and reach our eyes, causing us to perceive specific color. The UV spectrum shows the absorption of light at different wavelengths. The wavelength of maximum absorbance, lambda max, is related to the color of the molecule. Electronic transition. UV spectroscopy relies on the absorption of light by molecules, causing electrons to jump from lower to higher energy levels. It is nothing but electronic transitions. Chromophores. Chromophores are specific structural groups within a molecule that are responsible for its color. For example, an azo group can act as a chromophore, and its placement in a conjugated system can determine the color of the resulting compound. Specific functional groups called chromophores are responsible for UV absorption. These include pi electrons and are found in double bonds, triple bonds, and aromatic rings. Non-bonding electrons found in atoms with lone pairs such as oxygen, nitrogen, and halogens. Complementary colors. The color we perceive is the complementary color of the absorbed wavelengths. A molecule that absorbs a particular color will appear as the complementary color of the color wheel. For example, if a molecule absorbs blue light approximately between 400 and 490 nanometers, we'll perceive the complementary color, which is orange-yellow. Examples: beta-carotene. This compound found in carrots and other vegetables has an extended conjugated system and absorbs blue light, and the remaining yellow-orange wavelengths are transmitted, causing us to perceive it as orange. Chlorophyll. This pigment absorbs blue and red light, leaving green light to be reflected, resulting in the green color of plants. Quinine. A compound with a conjugated system, quinine absorbs blue and green light, appearing yellow. Aspirin. It is a colorless compound. This is general information about color in the visible spectroscopy. When white light passes through or it's reflected by a surface, doses that are absorbed or removed from the transmitter or reflected light, respectively. What is seen is the complementary colors, those that are not absorbed. This is the origin of color wheel. So we can have only the complementary colors. Organic compounds that are colored are typically those with extensively conjugate systems, typically more than 5. Consider beta-carotene. Here the lambda max for beta-carotene is 455 nanometer. That is, lambda max is 455 nanometer in the far blue region of the spectrum that is absorbed. But the remaining light has the complementary color of orange. It absorbs and it shows in the blue region, whereas the color is orange color. It's complementary. For example, when you take lycopene, the lambda max for lycopene is 474 nanometer in the near blue region of the spectrum that is absorbed, but the complement is now as red. When you take indigo, the lambda max is 602 nanometer in the orange region of the spectrum that is absorbed, but the complement color is indigo. Thus, when a sample only absorbs light of a single wavelength, the eye sees complementary colors. So these are all some wavelengths of some organic materials, and the color that we can see is exactly complement of violet. For example, when you take violet color, the range is 380 to 430 nanometer, but the color that can be seen by our eye, perceived by our eye, is yellow-green. Similarly, for this region, one can see only yellow, and green-blue, the complementary color is orange. For green, it's purple. For yellow, it is blue. For red, is blue-green. So this is complementary colors that we perceive usually. Most single sigma bonds, such as CC, CH, OH, all single bonds, and CO, have the change in energy del E values that corresponds to light in the deep UV part of the spectrum. They appear colorless to us because light in the visible region, 400 to 700 nanometer, simply doesn't have enough energy to excite their bonding electrons to an excited state. That's why water is colorless. This is why ethanol is colorless. This is why diethyl ether, hexanes, chloroform, and a host of other molecules which we encounter both in the lab and in the everyday life are colorless. The delay for the bonding orbitals is too large for relatively low energy photons of visible light to excite them. In fact, UV in the region below 120 nanometer is so energetic. It is completely absorbed by atmospheric O2 and N2. In UV spectroscopy, organic molecules absorb ultraviolet and visible light, leading to electronic transitions, primarily involving pi electrons and non-bonding n electrons, which are excited to high energy levels. The absorption of ultraviolet light by organic molecules always results in electronic excitation. Bond breaking can subsequently result if there exists ionization or bond vibration, but none of these processes are guaranteed to result from the absorption of ultraviolet light. UV spectroscopy is useful in the structure elucidation of organic compounds. The presence or absence of a particular absorption band at a particular wavelength may be regarded as an evidence for the presence or absence of a particular chromophore in the compound. In UV spectroscopy, the color of an organic compound arises from the absorption of light in the visible region, with colored compounds having extended systems of conjugation that cause their UV absorptions to extend into the visible region. Ruta-1,3-diene only absorbs in the UV region of the electromagnetic spectrum, but molecules with the larger conjugated systems will absorb from the visible spectrum and produce colors. For example, lycopene, which is responsible for the red color in tomatoes. Organic molecules contain bonding orbitals, sigma and pi, non-bonding orbitals, which is nothing but lone pair, usually designated by the letter N. In addition, they also have anti-bonding molecular orbitals, sigma star and pi star in electronic transitions in the molecule. Types of electronic transitions: pi to pi star transitions, absorption by pi electrons. N to pi star transitions, absorption by non-bonding electrons. And sigma to sigma star transitions, absorption by sigma electrons, less common in UV region. This increases the number of possible transitions that would involve electrons absorbing energy to move from the ground state, sigma, pi, and n, to an excited state, sigma star and pi star. However, even the lowest of these, pi to pi star, is within the UV region and therefore unlikely to give rise to a visible color without the effect of conjugation. The chromophore is the part of a molecule responsible for its color. This is usually a reasonable large part of the molecule, usually involving a conjugated system. So the possible electronic transitions are shown here graphically. So there are three transitions. So sigma to sigma star, pi to pi star, and n to pi star. And we have bonding, molecular bonding, sigma and pi, and we have anti-bonding, pi star and sigma star. That's the transition between sigma and sigma star, pi to pi star, and n to pi star. N is nothing but non-bonding. Examples: vitamin A has a conjugated system that spreads over pi C double bond C bonds. It appears as yellow. In the case of vitamin A, the gap between HOMO and LUMO has decreased to the point in which the absorptions has moved from UV to the visible part of the spectrum. To be precise, it moves to dark blue color. In the case of beta-carotene, the conjugated system spreads over 11 C double bond with C bonds. This reduces the gap between HOMO and LUMO even further. So the light absorbed decreases energy from dark blue 445 nanometer to light blue 475 nanometer. The color absorbed will be correspondingly higher energy, so beta-carotene is orange in color. Some of the absorbed colors and complementary colors are given as below. The green absorbs red, it's very small gap. Blue absorbs yellow, small gap. Violet absorbs greeny, yellow smaller and medium gap. Red absorbs green, medium gap. Orange absorbs light blue, large gap. And yellow absorbs dark blue, very large gap. Examples of colored molecules. Greens, chlorophyll alpha, it absorbs mostly in the red and blue wavelengths, having a reflected green color, indigo. It's a dark blue dye commonly synthesized to color blue jeans. Pansine. It is a violet in color. The compound is derived from shells of tropical sea snails. Carbonic acid is a deep red in color, produces in the scales of insects. Hemi B. It is a deep red in color, responsible for the transfer of gases in organisms with blood. Quercetin is golden yellow in color, found in saffron. Azo dyes. Molecules are based on the above structure, where R and R dash can be aryl and alkyl, which can produce very vivid colors. A typical azo compound is 4-hydroxyphenylazobenzene. The azo molecule has the ability to incorporate the lone pairs on the nitrogen atoms, which reduces further the gap between HOMO and LUMO. The delocalization of electrons in aryl azo compounds produce vivid colors, especially red, orange, and yellows. Some azo compounds can be used as acid-base indicators, methyl orange. In conclusion, the color of an organic compound is a result of its electronic structure, particularly the extent of conjugation, which determines which wavelengths of light are absorbed and therefore which wavelengths are transmitted and perceived by the eye. Organic compounds tend to be colored when there is an extensive conjugation, causing the energy gap between HOMO and LUMO to decrease, bringing the absorption band from UV to the visible region. Similarly, color is due to the energy absorbed by the compound when an electron transitions from the HOMO to LUMO.